Hello everyone. I hope you're doing well. So for today's class we're going to continue from where we left in the previous class. So in the previous class we did a couple of levels in the Turing complete challenge. We were able to see what a binary number is and how to represent a decimal number as a binary, in this case an 8-bit binary, and we saw that through this level, which is a binary eraser. We also did I don't remember this level, but we also did detect odd number of signals, and we saw an example of a circular dependency, which is an issue that's got from wiring the circuit in a wrong way, and we saw that we should avoid this circular dependency since it's actually an issue. So for today's class we are going to continue from here and do probably these counting signals, a half adder, which is something that is able to do calculation, that's addition, and find out what the delay lines are. So I hope you enjoy our class. The level says that the output component of this level is a binary counter, where the first 3 pins correspond to 1, 2, and 4. Use the binary counter to display the number of signals. Check this hint if you get stuck. A tip is the solution for this level is not very neat and requires more components. Okay, so let's first look at this. I think it's something that's able to increment, like you can see everything starts with 0, 0. This is representation of 0. This is a representation of 1. Oh, I get it. As we can see, only on this one we have 0 inputs are on. That's why the desired output is 0. And we also have the second one is just 1. Third one also 1, 2, 1, 2, 2, 3, 1, 2, 2, 3, 2, 3, 3, and finally 4. And oh, okay. So in order to represent 1, we just need a signal over here. This is 1. If we want 2, we can this should be 3 because it's 1 and 2. But if we just have this, that is 2, and that is 3, and this should be, the last one should represent 4. And if we want the number to be more, this is 6 and 7. but we're not having we're not going to use this. We want to use, because we have 4 bits, it's only 4 options, so our maximum will be just lighting up this. So let's try and figure out. The only hint that I've got is that the solution of this level is not very neat and requires more components, so at least that gives us the go ahead to do some things. Okay, so on the first signal, right now I'm trying to extrude these wires so that it's easier to build the logic from here. On the first tick, or the first condition, when everything is off, we want to have everything as off. So I think in this case we're going to use an AND gate. Let's try using an AND gate. Okay. Pick the first signal, second one, and third one, and also the final one. And based on that, that's alright. The output is that. And if we do light up the first bit, we should get 1. And 1 is lighting up this. So let's try using an OR gate instead and see where that gets us. Since if everything is off on this first tick, then everything is off. If our first bit is on, then we get a 1. If our second bit is on, just our second bit is on, we should still get a 1, and that's what we do get. First one, a 1, still a 1 regardless. And if either is 1, the first one is just 1, light this, still 1, light this, still 1, and light the final one, still 1, so that's okay. But now we need to know to check the combination whereby we have 2 of the bits lighting up. So for that case, we need to definitely use an AND gate. So if the first one is okay and the second one, so that's for 2 it's challenging, because for 2 we just need to light up 2, without this. So that's yeah, the only messy way I think of doing this is checking everything manually. So maybe let's try that and see where it gets us. This is for the condition where everything is on is the only time we get a 4. So that can be easy, since we can just use an AND get that's going to check that this is okay, this is alright, and the final one is alright, and another AND get to join them too. Yeah, and this is guaranteed going to work for displaying this. And if we have 3, that's going to be a challenge, since we have to say 3. We have to maybe check all the combinations of 3, and 3 is a bit tricky since this is 1, this is 2, so 3 is both of them. Okay. But 3 does not have a lot of combinations, so we can again say use an AND gate. This, and this. And not this, and not this. Another AND, but we have to not and not this is whereby we get 3, but 3 also we can have this and this. Okay, so I'm guessing we have to, I've got another idea, which is just to have everything as this. That So we just have so we have all these signals. We have the normal ones and the negated signals, and we kind of need to get a combination for all of them. So we're supposed to draw out 8 of these lines so that we can check the conditions efficiently. Okay, and so let's try moving some things around. And so that means that we can check every condition that we need. So if everything is off, we have a 0. So we can just pick the signals whereby everything is off, and that will probably just use AND gates so that everything is very strict. So one AND gate and another AND gate to chain it. Having this this is off, off, off. And this should also work for 4. I'm thinking so. By 4 I mean if all of these are on, this is on, this is on, this is on, and this is on. Okay, that's a problem. Yeah, it should be 4, just 4. And everything, if everything is off, get a 0. Okay, a 0 should not be a problem since it's mostly a 0. To get a 1, we need to light this bit up, and we have to make sure that at least just 1 is lit up. And for that, again we need to use, I think, an AND gate, and now chain where we have our bits as on, and that's that second one, third one, and the last one, and our final bit is this one. And now that satisfies whereby we have a 1, but also we can also have a 1 here. So that's again another condition we have to check, which is this, 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 and the last one, which is this, and finally chain them. So if the first bit, only the first bit is on, we get that. If that, and we need to, we're going to OR them. Let's not do that right now. And if the third bit is on, that means now we need again to check that condition, and we need an AND gate and another AND gate to make it larger gate. So for that we also need this signal. We're looking at wherever there is a signal. So second one, this is not on, so this should be our next one, and it's a bit hard to get it. This. Oh, we also have the first one, which we can pick it up from here, which is this, and our next one is this, which is hard to access, but we can get it from here, this line, and use it here. And there must be a last one, which is this is already taken. This is already taken. This is not yet taken. So this is the bit we are looking for. And that satisfies our condition for the first bit as just 1, the 1, not 2, just 1, 1, or 1, or 1, and not 2, and not 2, and not 2, and finally the last bit, which we can make its conditions over here, which is another AND to chain, and we just pick the bits whereby everything is lit up. And that's it. Can pick second. Let's create a bit slightly more space for things. So we have first one we can pick it from here. And second one also lit up, and we can pick it from this, which is this, and that should go to the last. I don't like this taking corners. I can probably just do this. So for the first bit lights this up and not any other combination. The second one takes the second, the third one takes the third, fourth one takes the fourth, and that's able to represent just this one. This is going to take a lot to do, so I'm not really sure if, so we can just use a pair of these. And another pair. And finally join the pair to or this, and that should give us a logical bit of 1. So that's a 1, that's a 0, but now we have to find for 2. So for 2, we can use the circuit whereby we did an odd number. So I'm guessing that if we create a circuit for odd number, is going to get us a 3. And the circuit was, let's see, an XOR. This is an odd number of signals. Okay, we can use an XOR and try to see if we are able to reduce our circuits. Maybe there is another hint based on what we did. Double trouble. Okay, this is exactly what we are doing. Okay, let's try chaining an XOR to be able to get an odd number. Okay. But in this case, a 3. I don't know what to do. Should we use the hints? Guess not. So an XOR together with another XOR and another XOR, and based on the 4 bits and not their inverse, which means we're dealing with just this, this, and finally this should give us an odd number of signals. Like if I have 1, it should light up, but already 1 is covered. So okay, if we have 2, that means it's an even. If we have 3, it's an odd, or 3, still an odd. If we have a 4, that's an even. So how do we use that in our advantage, that information in our advantage? Oh, I think probably we would need to, let's try and see. Oh, we're getting a 3 because it's still an odd and a 1, but we can also do an exclusive. Is it an exclusive? No. Check that it's one thing but not the other. Yeah, that's an exclusive. So maybe we can do an exclusive OR between the 3 and the 1 to see where that gets us. Because the only odd numbers we have over here is 3 and 1. But we already have a logic to get the 1, and we have a logic to get an odd number. So we just need to eliminate, and we only have 4 options, which are the 4 bits. So probably using another XOR gate. Okay. No, not an. Is it? Probably just. Okay, let's try using an XOR, but 1 is already determined. So probably this on the, okay, on the 3 we're going to eliminate the 1. So it's a bit hard. And I was avoiding to hard code everything. Okay, let's try another version, because let's use um, the knowledge we got from the previous class, which is we had 4 bits, and we were able to detect signals using odd number of signals using a chain of these XOR gates in this form. And this should give us an odd number. An odd number is either 3 or 1. So if we light 1, it's going to be 3. So this should light up 1, and even if we just pick up second one, still 1, another one, still 1, still 1, and that's okay. And we can do an elimination whereby we just get an even number. We assume that by negating an odd number, we get an even number, and an even number in this case is going to be 2. So which means if we have just 1, it takes out this root. If we have 2, it takes out this root. If we have any chance we have 2, it takes out this root. 2 takes out that root. And the issue is if we take 2 or 3, it does not do that. 4, still even, so that's all right. And but for 4 is a bit easier, so 4 we can hard code for 4. 4 we can just hard code 4, which is basically an even number. No, let's just hard code it since it's only this bit. So 4 is going to be an AND between, why am I using for all this? If this and this and this is wrong, and this, and finally the last one, we have to check them all with an AND gate. So only if all of them are on, that's a 4. So 4 we can just hard code. 4 is not a big issue. 4 is just okay. And 4 also satisfies an even number. So I'm not sure if we should check that, but let's just, because we don't want another bit lighting up when 4 lights up. So I'm not sure about that, but let's just assume 4 is already hard coded to this. But now we have odd numbers, which is 3. That means that it uses this circuit we created for odd number of signals and is able to light a 1, which is an odd number. And 2 should be even, so the current should flow through this other route if I drop either of these bits to have an even number. But the issue is that we have two of the odd numbers, and we have either one, which is all right, and yeah, we have one, and we kind of have to make sure that one bit is always off. So let's try doing another AND. So I'm just going to break the chain for this. So an XOR, we have 3. We want to detect between 1 and 3. That's our aim. So it's easier to detect if one of these this is tricky. Oh no. Oh, if this is true, we need to see if we have an extra bit that is off. So we can check. This is not good. For this case, I can just check this bit, but invert it so I satisfy the condition, and that means that this is a 3. This is a 3. Because if it's a 1, it's going to light up. Yeah, this is a way to detect a 1. And this is a way to detect okay, a 1, a 3, that's a 3. That's a 3. And a 1, that's a problem. So you kind of have to check all of these conditions. So I'll think need another AND gate, another AND gate for all those bits. Let's just keep them together. So we kind of need to extrude all these bits. So let's try getting out the nodes from each of these bits, their negation. And now since I have their negation, I can now check if I have 3. I need to differentiate. My aim is to differentiate between 3 and 1. And that's going to help me know when, since I already have an odd number of signals, but I have, among the odd numbers, I have 1 and 3 between the 4 bits. So I have to differentiate between them. And if 3 if 3, that means I need to light up it's tricky. Let me try doing this. So that detects 3. But we can also have these 3, which means that we also need to check that 3, and again we can have this was the first 3, we had our second 3, and we can have our next 3, which is this. And I'm guessing the final one should just be this. And so let's try and see. 1. That's a problem. Is there a gate that only checks if because if we have 1, we're getting 3. We have another 1, getting 3. Another 1, getting 3. Another 1, we're getting 3. So we still can't find a way to differentiate between 3 and 1, since if I use an OR gate between all these, they'll just be on. So, but the only thing I can see is that at least just 1 bit is always on. I don't know about the NAND gate, but let's just see what happens when you use an NAND gate. So this is the one. Turn it off. Another one. Okay. Another one. And another one. If we use 2, of course not. If we use 3, it does not light up. If we use 4, our main circuit takes up. If we use another combination of 3, still does not light up. So for some reason, which the NAND gate is able to help us, chaining these NAND gates is able to help us just detect 1. Only 1 when 1 of this. And now we can guarantee and say that this will be used to test a 1, to make sure that that signal is a 1. So apart from that, we need to know a 3. A 3 is basically let's try and create more space. A 3 is essentially just a 1, is essentially just an even number and an odd number. Okay, here is an even number. Here's an even number. That's the output. This gives us an even number of signals, but we need an odd number of signal, but which is not that is not the signal is not a 1. That's not a 1, but it is an odd number of signals. So it is it's not a 1 and it's an odd number of signal. So that guarantees us to have this as a three, but a 3 is 2. Yeah, that's tricky. Yeah, a 3 is 2 and 1 and 1. Oh no. Because now 3 is able to, that is 1. One is able to light that up, and 3 is able to light up this. It's a bit tricky. So we have a 1. We are able to detect a 1. And we are also able to detect a 3. But a 3, we can't just light up the second signal, which is this, because that's a 2. So we need to kind of light both of them up. So that's the challenge that and what's okay, maybe let's try doing an 2. That's the last thing we're supposed to do, since we already had coded the 4, and see probably what we discover from there. And a 2 is essentially, we have an even number that's not a 4. An even number that's not a 4. Let's try doing that logic. So we have a 4, we have an even number. Like if this, if we have a 4, that's an even number, that's not a 4. So if a 4, okay, so if even and not and let's just use a 2 input and. So if even, that's if it's even and not a 4, then that's definitely a 2. And we can test that and see. If we have, that's 3. 3 is the only one we're not getting. But if that's a 2, and if we just light, that's a 2. Also, that's a 2. Again, these are 3, which we are having a problem approaching or designing the 3. But for 2 is easy. We have a 4, and we can detect an even number of signals. So if it's not a 4 and it's even, then it's definitely a 2. And for odd numbers, if it's not a 1 and it's odd, that's what we did. If it's an even number, not an even, if it's an odd number, which is this line, and not a 1, this whole thing is to find out if it's a 1. If it's both of those, then it's a 3. So the only issue that I'm having is how to light up these 2, and I can't do this is a circular dependency as we saw. This is we need to light up this and the first one, and that's becoming tricky. Let me read the definitions again for these gates, and probably that is going to give us some hints of what we can use this. So again, An XOR checks if the inputs are different. That's an XOR. An XNOR checks if the inputs are the same. All of them to give a 1. And so let's just test our signals. Our first one. Oh, 0 is also even in this case. Wow. I don't know if the approach that we have taken is going to work. I can't really. So we have a circuit for odd number of signals. Let's find a way to eliminate this without messing things up. Instead of is a problem. Oh no. Let's probably just try the hint that they told us. It says the circuit for the 1 bit is the same as what you did in level odd number of signals. Okay, the circuitry of the second bit or choose bit is what you did in the double trouble, except when all of them are on. Okay, so again, okay, let's try another version and see again afresh. And For odd numbers of signals, we were able to use this. So for ones, in this level where we had double trouble, our aim was output green, which is an on, when two or more of them are green. Oh, when two or more are green. Okay, let's just start with this. When two or more, like we had one, which was not an issue, which was off. But when we had two, we had on. Three, we had on, and so on. Okay, so okay. That's when two or more. We're going to detect where two or more, and according to what we saw in double trouble, that was So first and second, first, and third, first, and fourth, then second and first is covered, second and second is covered, just one signal. Second and third, I don't think it's covered, which is second and third. So we need to do second and third, then second and fourth, which is still second, and nope, and fourth, and we can't have second. Then we go third and first, which is okay. Third and second, which is okay. Third, and third is not an option. Third and fourth, which should be our final one, which is third and fourth. And we have fourth and first, fourth and second, fourth and third. Fourth and fourth is not an option. So that's the circuit to detect. And now we need to OR them. This is to detect signals that are more than 2. They are more than, they're not 1. This is 1. One. These are 1. These are 2, 3, and 4. So for 1, that's separate. For 2, we can just pick up these. And the good thing is that it goes for still. Yeah, that was the biggest challenge, is that we needed a signal that's going to still kind of light up when this is 3. And now we can see that we have 3 and this is still lit up. And if we have 4 still lit up, but that's a problem. So we kind of need to get the 4 and ensure it excludes, like we can't have both of them as on. Okay, so let's just find first, second, third, and our final AND, which is chained as that. And now we are able to detect 4 and that's 3. So if this is on, we can't have that to be 6. So we kind of need to do something with both. Let's say, yeah, should be exclusive. So they kind of cannot coexist together. Right now we have I think we should use a NOT gate, if I'm not wrong. And an AND gate, so that we can check yeah, that means that okay, let's do this instead. Oh no, I think it should be part of the 2, maybe 2. And now if the signal is 4, that means this is negated, so it doesn't go through. But if it's above, like 3, oh no, what am I doing? That's a 2, which should not be the case. Exclusive NOR. But when we do 3, also a 2, that's okay. 2, okay. 3, 2, still okay. 3, still okay, but a 4 should fail. That means that if we have a NOT gate and have it plugged it here, the only time that fails is that, and that means that we now have that, and although most of these things is by trial and error, but now we have our second bit lighting up when we have 3 and when we have 2, and when we do 1, oh, that's a problem. We can't have this NOT gate. That means that to get a 4, we just take our signal from here, which is this, as normal. So 3, 3, and only when 4, so when we get a 4. And now we have finally our, how about our 0? Our 0. And now we need to detect a 1. Okay. And a 1, we are going to use the circuit we had for odd number of signals. Let's do that. For odd numbers of signals, we had to chain up XOR gates in this way. Goes to the first line, second line, third, and fourth. And now that's able to detect an odd number of signal, but we have an odd number of signal as 1 and 3 in this case. So we can just have our output flow. Okay. So that's a 1. And if we do a 2, that's a 2. Any combination of 2 is alright. 2 is alright. 3 is okay. And finally 4. And I believe we have had to finish. Like, that's done. The only issue here before was finding a way to light up this bit when the second bit for both 2 and 3. That was the challenge, but we used the circuit from the previous one, which detects at least 2 of the bits as on, and then hard codes the final 4, which is okay, and the other one is able to light up. So if we test, we should be okay. And this level took a long time, but I'm glad we were able to finish that level. And let's try doing this I don't know, it took a bit of time, so I guess we're going to do the half adder in our next lesson. So I'll catch you in the next one. Bye.